Greetings, colleagues. My name is Raj Manchanda. I'm the Chief Technology Officer for SAMPI North America, and I want to welcome you to our Space Applications Technical Committee webinar series. Please, if you can, in the chat, enter in your name, your title, your company name, and where you are geographically located. One more time, please, in the chat, enter in your name, your title, your company name, and where you are geographically located. Once again, welcome to SAMPI's Space Applications Technical Committee webinar series. We're fortunate to have Stan Bouslog today from NASA. He is going to talk on thermal protection systems, state of the industry. TC7 leadership includes Dr. Chris Fleming of Northrop Grumman as chair, Dr. Dan Polis of Sierra Space as vice chair, and PhD student Janin Palik of University of Nebraska-Lincoln. We encourage you to consider joining a SAMPI technical committee. All of the committees are available on SAMPI 365 platform, so you can consider joining obviously TC7 or any of the other SAMPI technical committees. The technical committees produced the State of the Technology Industry report, and we're working on the next edition. So as you join, please feel free to contribute to the next edition of the State of the Technology Industry report. My colleague Jordan at SAMPI is open to sponsorship opportunities. So if you're interested in that, please email Jordan, jordan@sampi.org, JOURDAN@sampi.org. There's a schedule of the remaining webinars coming from TC7. Again, we're very glad to have you here today. Please, if you can, in the chat, go ahead and enter in your name, your title, your company name, and your geographic location. I'm going to turn it over to our Vice Chair, Dan Polis, who will start the webinar. Thank you so much.
Thanks a lot, Raj. Yeah, and thanks everybody for joining today. We've really been trying to get more involvement in SAMPI's space applications, TC, and thought that this webinar series was a good way to draw people in on how materials are enabling space exploration. I'm really grateful that several NASA colleagues, former colleagues, have agreed to participate, and today we're lucky enough to have Stan Bouslog giving an overview of thermal protection systems. I met Stan really not during my government, during my NASA days, but just 2 years ago here, as he really was a great partner as the Aerospace started to do work in thermal protection systems, and he's been helping us significantly. So it's been a great partnership between NASA and the commercial space world. Stan is truly an industry expert. He's been working in thermal protection systems for 40 years, started out with a B.S M.S from University of Texas at Austin in Aerospace Engineering. And jumped into the analysis side of TPS, focusing on aerodynamics and thermal protection systems, as well as doing tests and hypersonics and arc jet tests. He then began managing thermal protection systems on X-33 and played a significant role in supporting the Columbia accident investigation. He served as the Orbiter TPS NASA systems engineer, and then went on to serve as the Orion heat shield subsystem manager. Today, he serves as the TPS Senior Discipline Expert at NASA JSC. So please welcome Stan. It's really great to have him. We're gonna let Stan kick off charts, and what I'd ask is that each of you, if you have questions, we'll save them for the end. Please put those questions in the Q&A rather than the chat. So again, please put your questions in the Q&A. We often get requests for charts. They will be available. We're recording this session, so they'll be available via this recording on the SAMPI 365 webpage, and that will be available in about 2 weeks. So with that, Stan, I'll turn the stage over to you.
No, thank you, Dan. And so, yeah, it's a, hopefully you folks can see my charts. Looks like they're being shared. And by the way, I'm here in Houston, Texas, and it's actually a sunny, beautiful day. So really happy to be here and talk to you a little bit about thermal protection systems. Um, so let me just, first of all, let you all know, here's, the outline of what I'm going to talk about today. Why, first of all, get off just with the basics. Why TPS? Why do you have TPS? What sort of process do you go through to select TPS? The types of TPS that are out there, and then talk a little about examples of flight-proven TPS, and then some other examples of TPS that's been developed but yet not flown. And then, of course, some of the current TPS challenges, and then sort of an assessment of where do we think we're going to go from here as far as TPS. So just to start off with, and a lot of you already know this, but those that don't, the reason you need TPS is because space flight really does require travel at very high velocities. To get started, of course, usually you need to launch off the surface of the Earth, and there's a launch vehicle that's going to take you up, and you have to accelerate up to orbital velocities. And so there's a lot of energy expended in those plumes to get you up to those velocities, so that's actually obviously heats up the base of these vehicles. So that's one source of heating where you will need the thermal protection system, especially in the base of the vehicles. And then if you're getting up into orbital velocities, well, orbital velocities are about 7 kilometers a second for low Earth orbit. And so to get up to 7 kilometers per second, you're going to need some protection against the aerodynamic heating on your launch vehicle. And then, of course, returning to Earth, you got to bleed off that 7 kilometers a second to land or to return to Earth. And so there's significant heating to that. So then if you go up to say, well, no, I'm not going to go to low Earth orbit, I want to go to the moon. Well, if you go to the moon, we're talking about 11 kilometers a second, especially during the return from the lunar vicinity to Earth. You're coming back at very high heating. So just to give folks an idea of what sort of heating we're talking about, actually convective heating actually scales with velocity to the cube, so 3 power. So that's just, you go from 7 to 11 kilometers a second. That's a significant increase in velocity and therefore a significant increase in heat flux. But there's not just convective heating. And most of you know that when you go supersonic and then hypersonic, you have a shock wave in front of your vehicle. That shock wave actually radiates energy back to the surface of the vehicle. It's not much energy at 7 kilometers a second, but you get up to 11 kilometers per second. It's very significant. And just the rule of thumb is that shock layer radiation actually scales with velocity to the 8th power. So that's the reason that, we look, if you want to go and participate in space flight, then you're going to have a vehicle that has some type of thermal protection or hot structures, and the hot structures we'll talk about in a little bit. So then it's like, okay, if I want to, come up with a vehicle and go to space, then, how do I select my TPS? So I just put together sort of a simple process here. The first thing is that you have to choose your mission requirements. And that is, you sort of have to know where you're going, how often you're going to go there, how much cargo, how much crew I'm going to take up. So obviously, missions could be to low Earth orbit, could be to the moon, or it could be out to Mars. And so you have to make a decision what those requirements are for your mission. And once you have, that sort of set, you kind of go, okay, well, what's more specifics about my mission? What sort of trajectories am I going to get there and get back? What does my vehicle look like? What's its size, its shape, et cetera. And then you go on from there as well. I need to generate a bunch of design environments. So like I mentioned before, rocket motors, quite often we use rocket motors almost always in space flight. And so they actually induce a fair amount of heating. So you have to worry about the heating that, and somebody's going to come up with those environments. Obviously, there's also aerodynamic heating and pressure on the vehicle, both during ascent and reentry. And there's the shock layer radiation that I mentioned previously. And then there's another thing that has really nothing to do with heating, but that is, if we especially go up to low Earth orbit, I think everybody's heard about the orbital debris there, and there's a significant risk of getting hit with micrometeorite and orbital debris impacts. And that does drive sometimes, what sort of TPS you choose. So once you have your environments identified, then you go through a material trade study and you make a decision. Is this vehicle going to be reusable or is it single use? What's the range? I could choose a material, but can it handle the environments that I've just predicted? And then, of course, you also got to assess what the cost is and the availability. And then so you say, okay, I come up with some options. Well, maybe there's no viable options. And at that point, you're sort of stuck to say, I've got to go back and potentially change my mission and vehicle design and go through some iterations there. But once you do come out and say, oh, I got some options, so then you can select your types of TPS you're going to use, and it could vary over the vehicle. So that's generally the process that people use when they're developing a space vehicle. So when we talk about types of TPS, there are several different key ones. I mean, first of all, if you're talking about a reusable TPS, usually it's an insulative system that sits on an existing structure. So you think of, you're building an aircraft back in the space shuttle orbiter days, which we'll get to in a minute. Obviously, it's an aluminum monocoque structure, and then I've got to put my thermal protection system on it. And so in this case, by definition, we're saying it's reusable. Usually we say, well, at least it's got to be reusable for at least 10 flights to be called that with minimal refurbishment. Not always, but quite often these systems are bonded to the structure. And then you got a structurally integrated TPS, and this is a little bit different. So in this case, what you have is you really don't have a monocoque, structure for the vehicle. It's actually formed by the outer layer, that it's part of the TPS system, and that's why we call it structurally integrated. So you actually have structural panels that are exposed to the environment. You still need an insulation behind those, and then of course they're often attached to stringers or beams within the vehicle, and quite often there in that case the fasteners are used to attach those panels onto the vehicle. And then you get hot structures. So what's different about hot structures is actually I'm taking my structural material, and it's on the outside of the vehicle exposed to the environments, and I don't necessarily have insulation right behind it. It's like the insulation's been moved to inside the vehicle to protect key components of the vehicle. And so that's why there's a little bit of a distinguishing difference here between structurally integrated TPS and hot structure. And then there's, of course, an ablator. An ablator is usually single use. I mean, some folks have tried to use them multiple times by doing some refurbishment, so scraping off the char or decomposed material on the surface and then flying it again. But that's not often done. But so essentially an ablator, its material is actually decomposing during the heating. The composition actually generates pyrolysis gases, which actually cool the bound layer. And of course, you usually get recession of the surface during flight. And as I mentioned earlier, it's usually single use, but it can be a pretty complex process, as that diagram there shows. There are other types of TPS, but they're actually not often used. I guess the dominant one here I can think of is heat sinks. Actually, in the early days of the X-15, they did use the structure, titanium and Inconels, as heat sinks as their TPS. but obviously, as they started increasing their velocities, they actually started putting an ablative outer layer on the X-15 even. There's also heat pipes and transpiration, but for the acreage of TPS, usually those are not used. And I will just, don't mean to put a plug for anybody else, but David Glass, he did write this very good paper quite a few years ago that gives him just an excellent overview of all these different types of TPS. So let's move on to, well, what's been proven, right? Obviously, the most one that's going to jump in front of everybody is flight-proven reusable TPS with a space shuttle orbiter. So we had 5 vehicles. They flew a total of 135 flights, and of course, the 3 major systems TPS systems on that vehicle was the high temperature tiles. And of course, that's the dominant, the black tiles that everybody thinks about when they think of the space shuttle orbiter. And then, of course, there's also blankets, that what we call the high temperature blankets were used on the leeward side, but also around the motors on the base of the vehicle. And then, of course, you had thermal barriers, which were prevalent everywhere. Anytime you had a door or an interface, there was a thermal barrier there. So all those materials are pretty much what we call state of the art. And in here, you can sort of see, the different flavors of the material systems that we used. Obviously, for the high temperature tiles, there are ceramic tiles. They were silica fiber based. And then at one point in time, we decided to change those tiles a little bit for enhanced properties, and we started, adding alumina fibers in there, and that's what coined the word of AETB, which is alumina enhanced thermal barrier. Actually, Boeing has a similar version of that, which they just call Boeing reusable insulation. And so those are a little bit stronger. They got a tougher coating on it than the space shuttle orbiter era tiles, but that's typically what is manufactured today. And then blankets, there's a couple different types. The lower temperature blankets are called frizzy, a felt reusable and surface insulation. They got a silicone coating on it. They're usually not good above 800F, especially for reusability. And then, of course, a frizzy is a little bit higher temperature material system. It is flexible. It's bonded to the structure, but usually there's a ceramic fiber and a silica fiber batting that's used. It's sort of like a quilted structure, if you will, and it's, as a thermal protection system. And I mentioned thermal barriers earlier. They are usually a ceramic fiber tube with a silica fiber fill. Sometimes they do have a Inconel mesh inside to add rigidity. But they are, there's several folks that actually produce those today. And as far as high temperature blankets, there's not a lot of folks out there that produce them, but the NASA TPSF facility down at KSC produces them, and Boeing also produces them in a company called High Temp. And by the way, I'm going to, throughout this pitch, I'm not going to give you every detail, just because I've run out of time, and I'm just trying to give an overview. And there's probably a few things I'm missing here. I did want to call out, though, as far as another vehicle that has flight-proven reusable TPS, and that is the Air Force X-37B. So if I got I think there's supposed to, it's classified now, so these numbers may be questionable, but what I understand is they've got 2 vehicles and they've flown 6 missions already. But essentially it's got a very, systems that are pretty much like a current type of tiles on them, and they've flown several times, and got to hand it to them for doing this. So moving on from reusable TPS, then probably the most used TPS is ablative systems. So I actually had to turn this into 2 pages as opposed to 1. But this is, again, I'm sure I'm going to miss a few, but at least the dominant bladers that are out there that have been used, I've hopefully captured here. Obviously, folks that are, follow Orion know that we're using the Avcoat material system that's actually produced by Textron. That was the very similar system was used in Apollo. And today, the way it's being made is into a molded block version, and that's what was flown in Orion Artemis 1. And so, that's essentially what the ablative system for Orion is. And I don't know if there's another application for that for the Avcoat right now. This has been the main one is for Orion. And then, of course, there's a really heritage ablative systems, and that's the high density carbon and silica phenolic systems. These were used on many of the planetary missions many years ago, and some of the more recent planetary missions. Also, of course, they were used in the ballistic missiles, where we all got started in a lot of TPS back in the 50s and early 60s. There's several different versions of this, but there's chopped or molded, carbon fiber versions. There's also tape wrap versions. And then, of course, folks also today are looking at 3D woven carbon fiber systems. So, and of course, you've got a resin, often a phenolic resin that's infiltrated into the fibers. So there's several different folks that, mostly for the DoD, that produce this material system. Northrop Grumman, Spirit Aerostructures, Textron, Solvay, etc. There's actually a good overview of a lot of the planetary missions in the reference there, and it's an NASA SP that gives you a pretty good idea of some of the missions that have used these type of ablative systems. Another system that's really currently available and a lot of folks are using is what we call PICA, which is the phenolic impregnated carbon ablator. Actually, it was, I think, probably the first use was in Stardust, but then it got used on the Mars Science Lab, and then of course Mars 2020. Mars Science Lab and Mars 2020 were almost a carbon copy, but that heat shield was about 4.5 meters in diameter, so a pretty good size heat shield. You can sort of see a picture of it there. So there are blocks of the PICA material that are bonded to the structure. So it is a carbon fiber preform that's been infiltrated with a phenolic resin. And as I mentioned, the blocks are bonded to a structure and the gaps between the blocks are then filled. So this material system was actually developed at NASA Ames. And so, people want to try to use that, they're going to have to go talk to NASA Ames. Another area that a variant of PICA is used is on SpaceX's Dragon capsule. So they did take the original PICA and modify it. One of the big modifications was, as opposed to a carbon fiber preform, they're actually using carbon felt and then infiltrating with the phenolic resin. But other than that, it's very similar to the PICA. And of course, where that's being used right now predominantly is on the Dragon capsule, produced by SpaceX. But, so there's other ablators out there. As I said, they're a pretty dominant factor in TPS world. So on the back shell of, the SpaceX Dragon capsule, they use a silicon syntactic foam. That was actually, that similar type of material system was also used in Mars Science Lab and in Mars 2020 in a lower heat flux regime, such as back shells, et cetera. So essentially, it's a lightweight silicon foam. It's RF transparent. Usually it's hand molded onto the structure and cured, or blocks are molded by hand, and then those blocks are bonded to the structure. So the SpaceX version of that is called SPAM, which actually stands for SpaceX Proprietary Ablative Material. But there is a company out there that sells something similar called AccuCell. So that's, silicone syntactic foams. They're usually used for the lower heat flux regimes. Another ablative systems is BLA, which is the Boeing lightweight ablator. And that is actually used on the Boeing CST-100 Starliner. And so it's a filled silicone resin that's hand packed into honeycomb and then cured. And right now, the availability of that material system is through Boeing. And then, of course, there's just a really, material systems that's been used for decades and decades is SLA 561V. This goes all the way back to the Viking and Pathfinder vehicles, the early probes into Mars. It was actually used in the shuttle external tank, et cetera. Essentially, there's a couple different versions. One of them is still a honeycomb version that's, you're hand packing your resin system into a honeycomb. There was also molded versions that made blocks that were then bonded to structure. That material system is available through Lockheed Martin. And then, into the world of launch vehicles a little bit, probably the predominant, TPS actually used for launch vehicles is cork. It's still used today. It's been used for decades. It doesn't, perform real well at high heat fluxes, but for lower heat fluxes, it performs fine. And of course, it's a natural material and usually have sheets of it that are bonded to the structure, and the gaps between them are filled. NASA Marshall actually took cork, modified it. They mixed cork and epoxy resin and microballoons and made a sprayable version of a TPS, and that actually was used on the SLS. So cork is typically available from Amarim, and of course MCC, which is produced by NASA Marshall. And then of course there's some other lesser known material systems that are used, especially in launch vehicles. One of them is a Pyron, which is a coated carbon felt. It's actually available through Zoltec, and that actually is used on the SpaceX Falcon vehicle. So enough about ablators. Let's talk a little bit about flight-proven hot structures. If you remember hot structures, so you usually have a structural material system that's directly exposed to the environments. The insulative package is usually not right behind the surface, but it's definitely you have to have insulation to protect the sub-assemblies or components within the vehicle. So what are the flight-proven hot structures? Well, clearly everybody thinks about the Space Shuttle Orbiter, and it's very true. We use the reinforced carbon-carbon on the nose cap and the wingletty edges. Some really good photos there of those, and of course that flew for 130 flights, 135 flights. It wasn't a single component that flew 135 flights, just to make that clear, though. But essentially, it was a carbon-carbon structure with a composite, essentially with a silicon carbide coating. There was internal insulation, and there was high-temperature metallic attachments to attach that to the vehicle. RCC is no longer available. However, there is a material system that is similar. It's called ACC6, and that's actually produced by CCAT. It's the carbon-carbon advanced technology folks out of Texas. But there's actually more recently, there's been another vehicle that flew with some hot structures, and that's the IXV, which is the Intermediate Experimental Vehicle by the Europeans. So this was a carbon silicon carbide material system, and most well known is in the nose cap they use that, but then also on their body flaps. And so there's a couple of good photographs there of that vehicle. But it did do a return from low Earth orbit successfully, and it did go through a whole development program. And today, of course, I think if you've heard the news, they're trying to take this vehicle and move it into an operational vehicle called Space Rider. And so there's some really cool videos about that on YouTube. And then if you get off into other systems that were developed, a lot of work was gone into developing these systems, but then they were never flown. So one that's near and dear to my heart, of course, is X-33 metallic panels. So those that remember, so the contract for the X-33 was let in 1996. So Lockheed Skunk Works actually won that contract. I was actually working at Goodrich Aerospace, which was providing the TPS for the X-33. So we were a sub to Lockheed Skunk Works. So that panel system was a metallic bond panel. Still had, you can sort of see in the pictures there, it has an insulation right underneath the high temperature metallic panel. And then it's got standoffs, so you can sort of see the standoffs there. And of course, those standoffs were attached to frames inside the vehicle. So this was, obviously if it's a metallic, you cannot take the real high temperatures of reentry, so you have to you're limited to a lower temperature system. But a lot of work was done on this. Matter of fact, all the thermal structural testing for qualification was completed, and a full ship set was fabricated. But unfortunately, the program was canceled due to a liquid hydrogen tank failure. So currently, this system is not available. People are on their own sort of making it again, but that's just sort of onesie-twosie type of folks. But the original panels, Goodrich is not producing any longer. Another key example, which is also near and dear to my heart, is the X-38, because I did work X-38, and that's the X-38 body flap. So this system was designed and fabricated by MAN Technology out of Europe for the X-38. It was a coated carbon silicon carbide, CMC, ceramic matrix composite. They did just tremendous amount of thermal and structural testing. And so the actual flight ship set was delivered by the Europeans to NASA. But unfortunately, the program was canceled. And so these never did fly. However, I will say that the material systems that were used in that are very similar to the materials that are now used on the ESA IXV, the Intermediate Experimental Vehicle of the Europeans. Then another system that some folks may know about, others may not, is called HEAT. HEAT actually stands for Heat Shield for Extreme Entry Environment Technology. So NASA Ames developed this system. They actually developed the material system and then also designed and built a 1 meter diameter engineering test unit. And essentially the system is a 3D woven carbon fiber with a phenolic resin infiltrated in it. This system actually is dual layer. In other words, there's a higher density outer layer, higher density of carbon fibers, and also of the resin. And then their internal is sort of a medium density insulation layer, as they call it. And that's just to reduce the total density of the whole system. They did do a lot of thermal structural testing, but unfortunately it has never flown. And so there is a good overview of that in the reference below. And NASA Ames produces that and actually owns the rights to that system. Another system that was developed is called the flexible TPS. So this system was actually invented out of NASA Langley. They worked on their HIAD, that's the hypersonic inflatable aerodynamic decelerator. So they help develop a flexible TPS, which actually it's like a Nextel fabric, the parallel drill insulative layers, and then a gas barrier layer in just so it's impermeable in the inside. And so I did say, this is not flown, but they did actually just fly a subscale version of their HIAD in late December of last year. I have not heard exactly how this performed, but so it does have one flight under its belt. And that material system is actually available through Jackson Bond Enterprises. But then I want to talk a little bit about TPS challenges. One of the things that people are not thinking about these days, and that is what I call changing the mindset. Most of you realize that previously for spaceflight, it was a government-operated vehicle for government-defined needs. So essentially, the U.S. government defined the mission, would select a design, fund the build, the development build of that vehicle, and then operate that vehicle. And also there tended to be not in a lot of flights. Spatial Orbiter was our heyday, where sometimes we were getting 4 flights a year. Everybody was, jumping for joy if we got 4 flights a year. So that, just with that type of mindset, that drives one type of thermal protection system. So where we're headed is clearly into the realm of commercially operated vehicles and to a more routine flights. And so once you do that, it sort of changes your mindset of what happens with the thermal protection systems. And so you're going to see that throughout the next part of this when I'm talking about some of the other key challenges. And one of them is supply chain. So the raw materials, a lot of the materials that are needed for thermal protection systems are very like specialty materials. They're not easily gotten. And there's very few domestic suppliers of these materials. And so that's a real problem. And then as we just talked about, we have the state-of-the-art material systems that have been developed and flown, but there's not really a TPS vendor. So how do you get the state-of-the-art reusable TPS? It's just not readily available. And then some of these systems, so especially limited for ablaters, it's limited to the government or to large aerospace companies, and that's another place to go get it. And then hot structures is actually, if you're want to develop a vehicle and you want to go get a hot structure, one of the things you're going to run up against is you're going to be competing with DoD's development of hypersonic weapon systems, and you probably won't get at the top of the list. So there's a lot of demand there, but it's mostly for the hypersonic weapon systems through DoD, and as a commercial space company, it's hard to penetrate that. So what happens, with the supply chain issues, et cetera? Well, one of the things is, commercial space companies are finding out, oh, I got to build my own TPS now, develop and build. I wasn't anticipating this. I'm going to have to spend a lot of money on the infrastructure just to provide that capability. So there is a cost impact to these folks, and clearly they could have impact in the development of new vehicles. The other thing is testing. There's not a lot of places you can go and get high temperature material property testing done. And if you can get in, it's very expensive, but you need those properties to design your vehicle. And then, of course, how do I check the performance of that material system? Well, I need to go to a test facility that does high enthalpy testing, such as arc jets. Well, there's only a few of them available. They're very expensive. And then, of course, if you look at radiant heat testing, there's minimal investment in making that happen. And of course, there's not a lot of guidance there on what is really required for TPS certification. And that goes back to, well, it used to be all dominated by the government. And so we did everything internally, but it's not real clear what the commercial space folks need to do. So the consequence of some of that is, well, companies sometimes they say, well, they just don't want to develop new TPS because it's too hard to get it certified, which is a very good point. Other folks are what they're doing is they're saying, well, I'm just not going to test much, and I'll just fly and see what happens, right? And of course, then what the impact is that you have potential flight failures. And then, of course, the last item is cost and production rates. To date, a lot of the TPS, development and installation and in manufacturing has been very manual. And that gets back into, well, if you're only, building a vehicle every so often, why bother to invest in automation or, in robotic systems, et cetera, because it's not worth the investment. So changing the mindset would hopefully have a big change in that. And so, if we start looking at what's going to happen now, I believe is that, people are going to say, well, I do need to produce TPS at a higher rate, so I can't do that manually anymore. I'm going to have to look at investing in a manufacturing infrastructure, which just is not available today. And then, a lot of times the systems are just not optimized for production. The other item too is there was a lot of focus in the government on improvement on performance, where obviously if commercial space companies are coming in, they're saying, well, yeah, I do need performance, but I really need to cut the cost. Well, the government, we never really delved into that. We were not trying to minimize cost. So that's another big change. But anyway, the consequences of where we're at today is that, you can have vehicle development in flight delays just because now the companies have to go off potentially develop their own TPS or build up the infrastructure to just resurrect the TPS that was built for the spatial orbiter, for example. And so the potential result of that is fewer companies will be successful. So then where do I think things are going? So this is pretty much my last slide. I think that the good thing is that NASA is incentivizing the development of commercial space economy, really moving out that for low Earth orbit. But I think rapidly that's going to expand to the moon and eventually to humans on Mars. So that's really good. So I sort of broke this up as, well, what do I think is happening for the different mission sets, right? Well, missions to Earth vicinity, that's low Earth orbit. Really, commercial space companies are driving these missions, and they need new, lower cost, readily available TPS and hot structures. And cost reduction is a major driver. They want reusable vehicles, and well, as opposed to flying it once or twice or 10 times, well, they want as many times as they can, and preferably 15 or more, 20 more flights before they have to really refurbish a vehicle. There's a lot of folks have been saying that they really would like to have lower cost coated ceramic tiles, but that's for right now. But in the future, they'd love to have ceramic matrix composites. But the problem is there's limited availability and they're very expensive. So right now, I think for missions to the Earth's vicinity, the focus is on reusable TPS and hot structures and advanced manufacturing, just advanced ways to make that so we can build up the production rate and reduce the costs. Then if you move out to missions to lunar vicinity, well, if you remember at the very beginning of this talk, I mentioned the heat fluxes and how the heat fluxes scale with velocity to the cube for convective and velocity to the 8th power for shock glare radiation. So the heat fluxes are going to be high when you come back from the moon. So probably going to need ablators because a lot of the other material systems are not going to be able to handle the heat fluxes or temperatures. But then you say, well, I need ablators, but okay, if I need to reduce cost, I just need to bring down the cost of ablators. So that's a key item there. And then, of course, also there's propulsive landings on the moon that are happening. That will drive, I think, a lot of the base heat shield designs. And I also put out the reusable lunar landers, and I could even say reusable first and second stage for the launch vehicles and done on here. But obviously, that's also going to drive the base heat shield designs. There are some commercial companies that are starting to establish a role in the lunar sample return and potentially also lunar crew and cargo transportation. Really, there's some mission design options and TPS innovation is needed there. Then I move on to planetary missions. Those flights tend to be less frequent. And so that's probably going to just result in that there's going to use the current ablator options that are already out there. And so NASA is going to be focusing on just maintaining the current suppliers, making sure those are available. As far as commercial space role in these planetary missions, I would say it's developing, and I don't think we understand where it's headed yet. And of course, that just means that the TPS needs are sort of TBD. But what we're seeing by this whole big picture is that we really believe that, well, just bottom line there, if you say innovation in the world of TPS and hot structures is just beginning. And I really believe that. But that's all I've got today. So hopefully that was of interest to folks.
Hey Stan, that was great. I thoroughly enjoyed it, and I've been working in this area, so still learned a lot, and it's great to see kind of the big picture of where we've been and where we're going. I see a few questions in the chat, which I'll get to in a second. I have a few as well, but just want to remind everybody, if you have a question, I think we have about 10 minutes for questions, so please enter them in the Q&A. I'll start with Mohammed Rui asked, he said, thanks for the nice overview, Stan. Can you please comment on conventional solutions to mitigate thermal short issues in structure integrated TPS systems?
Well, that's a good question. I mean, people obviously are looking at different types of ceramics, different materials for just I'll call it insulators between segments, joining issues. So they're trying to bring up the temperature of some of the materials at the joint, and then also ways to cut, to insulators to reduce that heat short. So that's a good question. That's a whole area of I think, of development, and we deal with that quite often. I just go back to spatial orbiter, and like we used high temperature Inconel 718, for example, for all the fixtures that are attached at RCC panels on the vehicle. So there's still a lot of that going on.
Thanks. Guy Larnack asked, what about the need of SHM for TPS? All capitals.
Safety, health, and we're trying to guess here at that.
Yeah. I don't know, Guy, maybe you can give us what SHM is. Structural health monitoring.
Oh, structural health monitoring. Yes. So really have not taken advantage of that too much, but I think that's obviously an opportunity for the future. I did not delve too much on instrumentation. We tend to use thermocouples still, and then of course strain gauges. But I know we're trying to, especially looking at fiber optic systems, so maybe we can get more real-time feedback. But that's definitely an area that we need to work on more. Let's put it that way.
Thanks. Robert Brushaber asks, how can SAMPE help with collaboration with the NASA and commercial space industry, contributing to the advancement of thermal protection systems and hot structure technologies, aiming to ensure national leadership and fostering innovation for the growth of the commercial space economy?
Yeah, I think, so there's always a need to develop new material systems. But I think as part of that, really have to look at the manufacturing, right? I mean, is it, how can we manufacture this cheaper, faster and cheaper? And that's, we need to figure out how to do that. So, quite often we've been, looking a lot at additive manufacturing. There's, I think, almost infinite number of solutions there that you sort of makes my head hurt to think of all the options sometimes. But when you do that, you think of a material system, but then you have to be compatible with your manufacturing process. And so there's a lot of iteration, I think, that has to go on there. But I think we need to get the production rates up. We need to get the material systems readily available. I mean, just to get a specialty material that's not commercially available can just kill you. So I think it's in that area. You need the material systems that are more readily available. And then you need really to link in with the manufacturing process.
Yeah, I mean, I guess maybe if I could just add on there, I feel like SAMPE could, try to have a thermal protection system symposium. And if you can get some of the people that are actively involved, again, it may be good for them to advertise, SpaceX's, Boeing's, Lockheed's, the Aerospace, what they're doing and what products they have available. It kind of increases the marketplace, and there's some startups out there. But maybe SAMPE could get a group of people presenting that. It makes people more aware. Let's see, next question from an anonymous attendee. Could you touch on a few of the pros and cons of using an ablator versus tiles as it applies to the back shell of human capsules? Is there any text or resource you could recommend for more info on this?
Well, yeah, there's probably not a single resource. I mean, obviously, it sort of depends on whether the vehicle is reusable or not, right? So that's a key part of it. I mean, you could make an argument, well, why do I need to put tiles if I'm not going to reuse the vehicle? But then if you go back and look at those environments, we did purposely put in their MOD impacts, the micrometeorite and orbital debris impacts. And a lot of times that will switch you one way or another. You will find out that sometimes tiles provide you more protection than an ablator against those impacts. And so not necessarily was tiles used there in that case for reusability, but just for added protection from impacts. Obviously, tiles are more expensive than an ablator. You can put on a real cheap ablator, and if you can handle the MOD impacts, then that would be a cheaper solution. In some cases, that's what's being done.
Thanks. Next question, what's the typical cost range of TPS materials, either approximate, ballpark?
Oh, God. Well, let's put it this way. Give you an idea. I'm not going to reveal any folks, right? But some folks came into us and said, hey, can you give us a ROM cost for putting tiles on our vehicle? And I misspoke, not putting, but the cost of the tiles. So for one vehicle, it was on the order of $35 million, and that was a bag of bricks. What I mean by that is uninstalled. So now, how much is installation cost? Maybe half that. So now you're talking for one vehicle, $50 million. I'm sure there was sticker shock over that, right? And people, so yeah, it can be easily be that kind of money for a vehicle. I mean, obviously, ablaters can be less expensive, but not always. So yeah, it just I know literally, you're talking $10 million plus for an Orion heat shield, right? And we're talking that kind of money, right? So yeah, they can be very costly, and that's why I think when you get commercial space folks coming in here, you're talking about how can we reduce these costs, and I think a lot of it gets into production. How can I reduce the material cost and can actually go to more of a higher production rate, which could also reduce your per item cost.
Thanks. Next question. Do you think there is enough research going on in ablator testing technology? Is there room for lowering testing costs?
Well, as far as ablaters, you could sort of see the page I got up here. I mean, right now, if going to low Earth orbit, I think folks are really looking at reusables, right? And that's where their focus is. Now, if you could find much reduced cost ablaters, then maybe that becomes financially, viable. But so going to the moon, right now to come back from the moon, you sort of, in my opinion, you sort of need that ablator just because it's such high energy reentry, unless you can figure out a different mission set where you can potentially propulsively slow yourself down enough that it's just, it's just like a LEO reentry, and that's a way to get away with maybe an alternate TPS system. But yeah, as far as reduction of test costs, I'm not sure how to make that happen. I know a lot of folks are investing, which is good, in what I would call lower capability systems. They call them plasmatrons. They're very good for screening of materials, but to get into a full blown arc jet, for example, it's hundreds of millions of dollars to build a new one. DoD is doing that, but of course they're not available to just everyone. So yeah, that's going to be an issue, I think, is the cost of testing.
Thanks. Let's see, what trends are being seen with radio frequency transparent TPS systems, both materials and processes?
Yeah, and I have not been following that real closely, but I know, for example, some of the silicon foams, they're using in the lower heating environments, but I know there's also, some other material system, even the CMC regime, that they're looking at that. I'm not personally real familiar with that, but obviously that's a need on the DoD side, a little bit of a need on the NASA side, but I don't personally know a lot about it myself.
Maybe let's take two more questions here. So regarding cost, which steps of the production process are driving the cost today?
Ooh, boy, that's a really good question. I think we need a what do they call them? Six Sigma event to go figure that out. But yeah, they can happen in several different areas. I mean, part of it's just the manual aspects of doing it all. We tend to do that just because production rates aren't that high. So production, just of the bake system that's going to be attached can be pretty high, but the installation can be pretty high too, especially for bonded systems. If you're individually bonding, blocks or tiles onto a vehicle, that's pretty time consuming. I think, if we can get into fastening, obviously fasteners go a lot faster than a bonding. So, I think a really good assessment, a lot of that needs to be done.
Thanks. And then last question, do you think some of the difficulty with testing is due to high temperatures, heating rates we try to test against? Have you seen cross-industry cooperation to expand testing services?
Well, I do think, yeah. I mean, part of it is just because you got the high temperatures, right? And of course, you're pretty demanding on a space vehicle to try to getting a really good material property set, right? I mean, if I'm just building insulation to go inside of a furnace, for example, there's a lot less I need to know about that material system as opposed to putting on a vehicle that's a structural member. And so I need a lot more, high temperature material property data, and that's, not only the thermal property data but the mechanical property data. And so to get that at temperature is really hard. So there is some, I think they are expanding some. There's NASA and DoD actually are investing in a few folks to develop that capability. So I think there is going to be more of availability of the high temperature material properties testing. But yeah, it's those are not easy tests. If I'm saying, I got to go do tensile test at 3000 F, that's not easy.
Yeah. Well, I think that we're about at time. I think probably I was going to put up one public service announcement. I'm assuming Raj may want to say a word, but Stan, thank you so much for really taking the time to, put this together. I know it's not kind of part of your day job, but going the extra mile to reach out to the community. It's great because it gives us some targets to shoot for. And I really appreciate the partnership that you reach out to the industry partners as well. I guess one service announcement, we already have the next talk in this space application series planned for December 13th, Wednesday. Jeremy Jacobs will be giving a talk on certification of composite structures. That'll be a good one. So I hope you all will join us then. Please register at NASA, at SAMPE 365, sorry. And then I was going to say also, if you have any interest to join the TC, hopefully you're seeing my page. Here's some contact info for you. You can either contact Chris Fleming, our chair, myself, or Jaden Pollock to join SAMPE 365 Space Applications TC. And with that, Raj, anything that you wanted to add?
No, just wanted to thank Stan again for taking time out, and Dan for you to organizing and identifying Stan. But SAMPE's here for you. We have community, and we're very willing and able to move ahead. So I think, Dan, your idea of a possible symposia, something like that, we have SAMPE Long Beach coming up. So we might be knocking on Stan's door again to help organize a panel or something like that. And that's something we can do, not too far away, but our community is ready to advance the technology.
Great. Thanks, everybody.
Thank you.
Thank you, everyone.